Saxon Advanced Mathematics, Lesson 56. Students, this is a three-parter. It's kind of a long lesson. It's not horribly difficult, but there's just a lot of material. So I'm going to experiment with teaching this in a slightly different way, and then I'm going to ask you guys to give me feedback when we talk at the end of the week about whether it was helpful or not, when we video chat. Okay, there are three topics. None of them is particularly earth-shaking. None of them is a huge new concept. So what I'm going to do is I'm going to try to minimize the amount of detail I give you because I think you can easily figure it out, all right? Instead of doing all the calculations, I'm going to show you a minimum of calculations and see if that just helps this move a little more quickly. Not that we're trying to rush, but so that you don't get bogged down in a really long lesson. Because if I taught this one straight through, it would be at least 45 minutes. I have no doubt in my mind. All right? So before I turn it into 45 minutes of me talking about how I'm trying to make it shorter, let me stop saying that and say, give me your feedback. If need be, I can reteach it, but I really think we'll be okay. All right. Part A is about triangular areas. Now, you know how to find the area of a triangle. It's base times height divided by 2. The base is always easy. The height is the part that's tricky because, this is the way I always teach it, you send your spider up to the top and he has to drop a straight line down. This is the height, right? It has to be not the sides necessarily, but a height. And if you've got a triangle like this, it becomes even trickier. This is my spider. Because he has to drop it down on the outside, doesn't he? Pretend those aren't overlapping, right? So that's the tricky part of finding the area of triangles. So what happens, and John has always been nice to us because he always gives us that measure. So what happens if we have a triangle like this, and we're asked to find, this is in inches, not that it matters. What if we're asked to find the area of this triangle? We go, okay, base times height divided by 2. We've got the base, but we don't have the height. So we send our spider up. I don't know why, you guys, I just have to have that spider up there. What we need to find is this measurement. Then we can do base times height, right? Well, we know how to find, if we ignore this part of it, this is a right triangle, and we've got the adjacent side, and we've got the hypotenuse, and we've got the size of the angle. We just need the opposite. So we know that the sine of 42 degrees will equal the opposite, which we don't know, over the hypotenuse, which is 12. And then we just bump that up. 12 times the sine of 42 degrees equals, where is it? 8.03. That is a computer calculation. Remember, you put in the 42, then the sine, then times 12. Now we've got, this is the height. So now we do 16, the base, times 8.03, the height, divided by 2, and there is the area of our triangle. Okay, so the trick here was to use the trig function to find the height. Now, what we're going to do is just apply that to two more scenarios. One is going to be like this, and I'm just going to show you that one in the book. I'll draw it because that's easier. It might take me a minute longer, but 56.2. This is a really whack looking triangle. It's like this. Okay, we're supposed to find the area of this. It's 14. Pretend that's perfect. It's 6. It's 150. Okay, so what we need is this, right? Because we need to find the height. We need this. So we want to look at this triangle like so. We know that this 14 is this edge. So that is the hypotenuse in this new triangle that we're looking at. All we need to know is what this angle is. And we know that's 150, so this has to be 30 degrees. So this is the hypotenuse. We want the opposite. We've got the angle, so we can say the sine of 30 degrees equals the opposite over the hypotenuse, which is 14, right? It was a side on the old triangle, but when we drew this new one in, it turned into the hypotenuse. Flip that around, we go 14 times the sine of 30 degrees, and that comes through to 7. According to John, it comes out even. That's crazy. Now we're ready to do base times height divided by 2. The base is 6. The height, even though we measured it way out here, that's fine, equals 21, and this is meters. Okay? And then the last one, I am basically doing these. I can never say no to a good math problem, you guys. This is a trapezoid. And remember, the way that we do these is we are going to divide it into 2 triangles. Let's do it the same way John does in the example, just so we're clear. We want to divide it like that. We've got the base of this one. We've got the base of that one. We just need the height for both of them, which will be, I'll make it bolder. That's the height that we need. And then we need, that will work for this triangle too, right? Because it'll be the same as this. So, but we want to measure it first down here because we want to use this guy as our trig triangle. Notice this one was on the outside. Now we're back in the middle. And even though it looks like we're making a different triangle, which we are, that's okay. We're just trying to find the height because the height will tell us about this triangle and it will tell us about this triangle. So this is the opposite side. That's the hypotenuse. I'm going to do my shortcut. 5 times the sine of 29 degrees will give us the height, if you will. And that is, the height equals 2.42. So now this is triangle A. We don't have to think about this triangle anymore because we used that just to get the height. We now have it. Now we can change our focus to this triangle, which still has the same height. So now we'll do base of 10 times height of 2.42 divided by 2, because triangles do that. And then we'll add to it the base of this guy times his height, 2.42, again divided by 2. This comes down to 12.10. This is 4.84, sorry, I can't talk. You can run these through your calculators and make sure that they all make sense. And so our total area is these two added together. It's 16.94 meters squared. Yay. All right, that was a little bit fast, but I hope you could follow. All right, part B. Areas of segments. This is one like the other one where it's not that hard, it's just a tiny bit tricky. Okay, what we've got here, we're talking about segments, circles. Okay. Just to firm up our vocabulary rather. A sector is like a pizza slice, right? It's straight on the edges and it's curved on the end. Ooh, pretend that's perfect. That's a rough circle, you guys, and that's messy too. Sorry. The sector is the whole thing. We know how to calculate sectors. Usually, we take the central angle, over 360, and then we multiply it. Oh, I don't want to use x. I'll use this. We're multiplying it by pi r squared, because this is the area of the circle, and this is the size of the sector, right? It's the proportion of the circle. So this is the formula that we can use to measure this whole pizza slice. But in these problems that we're doing, John wants us to find what he calls the segment. Okay? This area is what John calls the segment. Okay? The sector is the whole pizza slice. This segment is the little bit at the end, but notice that right here, ooh, it's not very neatly drawn. That's making me sad. This is a radius, this is a radius, and this is the height of our rectangle. Okay? This is the size of the angle. It can be measured in degrees, but the central angle, this bit here, can be measured in radians. Ooh. In radians or rads. And remember, so then we would put the central angle, again, measured in radians, that's fine. Now, instead of being over 360, it would be over 2 pi. All right? So that's another little spin we can put on these problems to make them a little bit more confusing. So let's try a problem. Example 56.4. I'm going to use my space. It'll probably be confusing. It's nice of me to say so, right? Find the area of the segment shown above if the area of the sector... Oh, wait, sorry, I stopped reading. I skipped to another part. If the central angle is 0.6 rads, and the radius is 10 feet. Okay, so we're setting up this calculation, right? So we need the central angle is 0.6 divided by 2 pi, because that's the full circle, right? 180 equals pi. We've got that memorized. So 2 pi is the whole circle, and we want the whole circle. Okay, so that's the size of the sector. And then we multiply this times the area of the whole circle, which is pi r squared. So we have to multiply it by pi times the radius squared. So that's 100. And I'm going to put that over 1 so I don't get confused. So now look what happens. The pi's cancel. Let's multiply this by this. This will make it 2 decimal places bigger, so that becomes 60. 60 divided by 2 is 30. So what we find out is 30, we're in feet squared. This is the size of the sector, okay? So this is the whole slice. What we need to do, I forgot to tell you this way back at the beginning. If we want the segment, we have to take the whole sector and subtract the triangle. And that will give us what we call the segment. Okay? This little skinny bit is the whole pizza. This is like the crust, right? After you eat off the good part of the pizza, this is like the crust. So that's exactly what we're gonna do. We're gonna cut the whole slice of pizza, and then we're gonna eat the yummy bit and trim off the crust. And the crust is what we call the segment. So this is our overall game plan. I'm sorry, I forgot to mention that before. I was so excited about this other stuff. I was excited about the Radians, I won't lie. Okay, so what we found out is that the whole pizza slice is 30 feet squared. Now we have to subtract out the triangle, right? So right here, I'm going to work on the triangle. The base of the triangle, we know, is 10, because it's the radius, right? So that's the base. Now we have to multiply that by the height. How are we going to find the height of the triangle? Well, that's what we learned in the first part of this lesson, right? We learned that if this is 0.6 radians, then we can use that to find the height. And I'm going to switch to another book so I can do that calculation on a separate piece of paper, all right? So what we're doing is we want to find the height of the triangle, all right? We know that this, here, I'm going to draw that triangle over again. It's not completely. This is 0.6 rads. And that's all we know, right? Oh, we know that this is 10, right? Because that's that. This isn't 10, but that is. So the hypotenuse is 10, right? For this little triangle we've got going here. So the sine, because we want this side, right? We want the opposite, which we're going to call the height of our triangle, not the hypotenuse, but the height. We're going to say that if we take the sine of 0.6 rads, that will be equal to this height, which is equal to the opposite, over the hypotenuse, which is 10. Make sense? This is what we just did at the beginning of the lesson. So now we can rewrite that as something else I should tell you. 10 times the sine of 0.6 equals the hypotenuse. You can calculate trig functions in radians by toggling on your smartphone to switch it from degrees to radians. Then you don't have to hand calculate the difference. I very much wish I could show you that right now, but my calculator is busy being a camera. But see if you can see the place on your smartphone. It's usually in the upper left. You can toggle back and forth between degree or radians, and it usually says the word in the corner of the screen. If not, what you can do is you can adjust the 0.6 radians to degrees by multiplying it by 180. But I really want us to start working a little bit in radians. Let me just see if John gives it. No, he just gives the answer as 5.65, all right? We'll talk about this and I'll see if you figured it out, but you should be able to adjust your calculator. And then whenever you're doing these calculations, you can choose degree or radians. Okay, so that's one little hiccup that may be messing you up, but otherwise this is just the calculation we were doing. We're doing it in radians. This is the length of this height. So now we can take it back over here. It's 10 times 5.65, this is base times height, divided by 2. That tells us that the area of the triangle equals 28.25. Okay? Feet squared. I'll squeeze it, feet squared. Now for our final calculation, I'll go back to my separate page so you can see that. So we're taking the sector and we're subtracting the triangle. The sector is 30 feet. And we're subtracting the triangle, which is 28.25, which tells us that is the segment, the pizza crust, right? This is the whole slice, and this is the triangle. Okay? I hope that makes sense. These are kind of fun when you start to understand how the pieces are flitting in and out. All right? I hope I didn't confuse you by using my book and all of that stuff. But it helps me keep everything on one page, and I wanted you to really be clear on this. Okay, the only part I feel uncomfortable about it all is just making sure you understand how to go back and forth between degrees and rads on your calculator. All right? All right. The last section of this lesson is completely unrelated, but it does relate quite nicely to something that we did last year in the Red Book. It's the exact same thing, to tell you the truth. Systems of inequalities. In these problems, I'm going to show them to you. It's down at the bottom here. In these problems, we are given two equations. We're told what shape they make, and John has even been so kind as to graph them for us, right? Here's the line, and here is the parabola. What he's asking us to do is to identify which region is indicated, because these are actually inequalities. Now remember that when y is greater than x, we choose the region where the region indicated is above the shape, and when y is less than, we choose below the shape. So let's just take a look at this. And these are very intuitive, you guys. Trust your ability to get this, and then I'll show you how to test it in the end. Y is greater than this, and we see it's the line. So we know, okay, it's this. If y is greater than, then the area of the solution would fall above the line. Okay? That's where the solution is, because y is greater than the line, so it's up. Here it says y is greater than the parabola. There's the parabola. So again, we want what's greater than the parabola. So that's outside of the parabola, right? The inside the parabola only goes down. We want the outer areas. So we want above the line and outside the parabola. That's area A, right? We think that is the region where the solutions to this system of inequalities will lie. What we do is we choose a test point, which is any point clearly within the region that we're interested in, A in this case, and well outside. Pick nice numbers. That's what I'm trying to say. Pick nice numbers that you wouldn't mind forcing through these. Then what we do is we use this test point, X and Y, we plug it in and see if it's true. I'm not going to go through those calculations in detail. John shows you right here. He plugs in, see, here's the original inequality. He plugs in 5 for Y, 0 for X, and then he tests to make sure that that comes true. 5 is greater than -4, that is true. Then he does the same point and pushes that through the equation for the parabola. Or it's not an equation, it's an inequality. 5 is Y, and then there's where he's plugged the 0 in. He gets 5 is greater than or equal to -1. That is also true. That confirms that region A is indeed the area where both of the inequalities are true. So the solution is region A, and then he just talks, don't worry about the solid lines and the dots. That's covered in the next problem. All right? The next problem works exactly the same. John gives us most of these. So actually, you guys, there's very little you have to write down, which is nice. We have a parabola, whoop, and we have a line. And there it's a dotted. And we go, what the heck is up with the dotted line, John? And he reminds us that in this case, the inequality is just less than. See, it's not equal to. It's just less than. So remember, that's how we graph when we're only showing less than or greater than and not equal to as well. We just use the dotted line. So that's okay. He remembered to graph that. We don't have to. We just take that into consideration as we're choosing our answer. There it is. Okay. So again, when y is greater than the rest of the equation, we generally think up. When y is less than, we generally think down. Use your instincts. And again, that's why we test each point, is to make sure our instincts were good. Y is greater than the parabola. Okay, so there's the parabola. It's facing up. So y is going to get greater as I go up. So that's inside the parabola, not outside. Okay? Last time it was different, but that's because our parabola was facing down. So it's a little head trippy, right? Y is greater than, so that means up, so that means inside the parabola. Y is less than the line. Okay, there's the line. We want the less thans, so that is below the line. So it looks like what we want is area C, right? Inside the parabola, below the line. We do the same thing. Once we have our instinct, we choose a point. And again, it can be any point in this area C. Just make sure that your point is clearly within. Don't choose something that's on the line. That's the only trick. Choose something that's in the line, choose nice numbers, and then just like we did last time, run that point through both equations and make sure it comes out true. If it comes out false for one of those, that means you either made a mistake in your math or you chose the wrong region. So check your math first is what I would do. Make sure there was no silly mistake. And then if it looks like you really were wrong in choosing the region, then go back and re-examine that. Did I choose wisely? What else could it be? Okay. And then there's one more problem of these. Again, which region contains the coordinates of the point that satisfy the given system of inequalities? We've got a circle and we've got a line. Now, when this side, when the x and y are less than, that means inside the circle. When the x and y are greater than, that means outside the circle. So this one looks like inside the circle. So that eliminates A and D. We know it has to be either B or C. And then y is greater than x, so that looks like it's above the line, right? Again, choose a point in your hypothesized region, right? Choose a test point that is clearly within that region. Don't choose anything near the edges because that can give you an ambiguous answer, and that's the last thing we want. Choose a nice point with cute little numbers and then run it through both of the equations. Make sure it comes out true. And in this one, indeed, it's region B. That makes sense because it's inside the circle but above the line. Okay, I hope that wasn't too fast. I hope you feel like it makes a certain amount of sense. And again, I want to talk to you on Friday about whether it's helpful to push through a lesson like this a little more quickly so that you don't bog down in sitting here forever, or whether, no, you really do prefer to see all the details. Okay, 56 is history. Thank you and goodbye.